Having seen the various signals that are generated as a consequence of interaction of electrons with specimen in a TEM or in an SEM, we will try to understand the phenomenon of scattering from a classical view called as the Rutherford scattering cross section, where we start with looking at an isolated atom, and as a consequence of the interaction of an electromagnetic radiation with an isolated atom, if we start arranging this in a crystalline form, what kind of changes happen? The interesting thing is, this draws me back to the classic experiment of Rutherford, where he checked the gold foil, the classic experiment of Rutherford, where a gold foil was bombarded with a fast moving alpha particles, and the signals raised were studied based on the angle of scatter. So let's look at the classic experiment where the foundations of this idea of scattering lie, where the Rutherford gold foil experiment was conducted. So the idea is, you have a schematic of a setup like this, where a gold foil is impinged with a beam of alpha particles, and you are collecting the signal of the alpha particles which have undergone scattering across a screen which is surrounding the gold foil, as you see in the schematic. Now, why is this important? The consequence of scattering, or the consequence of the interaction of a charged particle with a stationary object, has been related with the angle of deviation from the primary source of particles. Based on this, a link between the angle of scatter and the scattering event has been established. If I want to understand this, think of a thought experiment where an isolated atom is hit with a fast moving electron beam. The gold foil experiment tells us that a successful scattering event can be defined by a deviation in the angle of the electron beam after interacting with the isolated atom. Now, what is interesting is, the success of a scattering event can be defined by the probability of having a deviation in the path of the electron beam that has interacted with the specimen. This has a specific term called as the scattering cross section. Now, when I look at it specifically in terms of definition as a cross section, think of the event of scattering something analogous to a situation where I have a target and I want to fire a bullet at the target. If I fire a bullet and it exactly goes and hits the absolute center, I know there is a successful collision that has happened. The probability of me successfully colliding with the target depends on the angle at which I am launching the bullet here. So, I have a range of angles which define whether or not I have successfully hit the target. Likewise, from the concepts of the Rutherford gold foil experiment, the definition of a successful scattering event is given by scattering cross section, which simply means the probability of having a successful collision. So, if I think of a charged particle hitting a target, I can always draw a comparison between the surface area of the particle and the surface area of the target where I have the collision. And once there is a successful event, I have a deviation in the angle. Now, let me take an example from a schematic from this classical text on electron microscopy. So, with this example schematic from Williams and Carter, let me try to explain the probability of a successful scattering event. As a matter of collision that has happened with an incident electron beam or a charged particle colliding with an isolated atom, let us say the deviation in the angle that is caused is theta. I have a small differential angle where I can relate the planar angle or angle along a unidimensional ray to the solid angle which is over a volume which is spread across with a differential d theta over d omega. This gives me the scattering cross section from an isolated atom, and scattering cross section means not a physical cross section like a specimen that I was talking about some time ago, but the probability of having a successful collision event. Now, when an electron undergoes a successful scatter, a successful forward scatter, this angle is lesser than 90 degrees. If the electron interacts with an atom and it goes really close to the nucleus, because of the strong Coulombic interaction of the nucleus and the electron that you may have a complete deviation in the path of the electron beam and it goes backward. These kind of cases have been recorded in the Rutherford backscattering experiment as well, and that is where the idea of backscatter comes into place. When there is a strong enough deviation because of the interaction with the nucleus and the incoming charged particle, you have a defined angle of scatter. When the interaction is weak, you would have only a small angle of scatter. So, the terminology related to scattering is, like I was mentioning, the cross section. It is not exactly the physical area, but on a small charged particle colliding with an actual area of an atom gives us the probability of successful collision. And this is defined as the differential cross section that I have shown you in the previous schematic, where if I have d sigma is the scattering cross section, this ratio of d sigma over d omega times the d theta, which is the small differential angle of deviation, if this is integrated by taking into account the complete total number of atoms that are present within a solid, where I have the Avogadro number of atoms, and I multiply it with the density and the thickness of the sample divided over the area of the specimen, I end up getting the scattering cross section. This sigma total times the thickness is the probability of scattering for a specimen which has a thickness, and here is the origin for the mass thickness contrast, which we will see in the bright field imaging in the next lectures. There is one important parameter called as the mean free path. The mean free path is defined as the average distance an electron travels between two consecutive scattering events. For example, if I have a thick specimen and I have the first scattering event as soon as the electron enters the specimen, over a distance, if I have another successful collision with another atom lying at a depth, this distance that the electron is now traveling is given by the mean free path lambda. This is a very important parameter for inelastic scattering events, specifically when I want to look at inelastic scattering cross sections, which can in turn be a signature of the thickness of the specimen, and it is extremely important for electron energy loss spectroscopy. So, the mean free path from the scattering cross section can also be defined as 1 over sigma total, which is an inversion of the area over the Avogadro number times sigma atom, which is the atomic scattering cross section, times the density. For typical TEM accelerating voltages, this is in the order of tens of nanometers. At the top of my head, I can tell you that silicon has a value of something around 130 nanometer, similar range for aluminum, and carbon has closer to 200 nanometer, whereas heavier elements have much lesser, copper, gold in the order of less than 25 nanometers and copper around 60 nanometer or so. These are not accurate numbers, but just to give you an idea that the scattering cross section increases with the atomic number, whereas the mean free path decreases with the increasing in the atomic number. So if I have to define the Rutherford scattering cross section, here is what we have. The scattering from an isolated nucleus has been defined as a function of the angle of scatter, which is dependent on the atomic number, the charge of the particle, the accelerating voltage that you have, multiplied by the differential scattering cross section that you have here. Now if you look at this particular expression, there is a small problem. How do you define scattering for the direct beam that is not deviating at all from the principal axis? If my theta becomes 0 here, this expression becomes undefined. So if I look at the issues with this particular scattering cross section expression, which is derived from the, or which has the origins in the classical gold foil experiment, this equation neglects or ignores the relativistic effects. You do not account for the change in the mass of the electron as the velocity is reaching the values close to the velocity of light. You are neglecting the screening effect of the electron cloud. So you are simply looking at a strong positively charged nucleus interacting with an electron beam, and you are only thinking about the particle nature of the electrons. Again, I will not go into the details on this right now. In my view, you cannot really distinguish the wave nature and the particle nature. There are corrections to this when you look at the wave nature of the electron and introduce the projection potentials where the foundations for high resolution imaging are laid. So I was mentioning that the previous expression does not account for the screening effect of the electron cloud, and it does not account for the undeviated beam, which has an angle of incidence as 0. So to account for this, there is a screening factor or a minimum angle theta naught which is introduced, where if the angle of scattering is greater than this theta naught, the electron-electron interaction or the electron-electron cloud interaction is negligible and the electron-nucleus interaction is dominant. But for this angle lower than this particular value, the screening cross section can be given as something proportional to the square root of accelerating voltage inverse. And by introducing this, as the angle of scatter is tending close to 0, your scattering cross section is no longer undefined, and typically for copper at 100 kilovolt, this theta naught has a range of approximately 2 degrees. By introducing this screening parameter of theta naught and the previous expression together, you now have a sort of a reasonably well defined scattering cross section, and this is what you end up with. If I look at the graphical representation of the scattering cross section as a function of energy and the scattering angle for different elements, you end up with something like this. For copper at various accelerating voltages, the scattering cross section, by the way, I forgot mentioning the units for the area of for the scattering cross section. The concept of the cross section is the area on the surface of the atom which can collide with a fast moving particle to give you a successful collision. So it is defined as square meter, or there is a unit called as barn. So the scattering cross section is measured in barns or in meter square, and for copper at 100 kV it varies somewhere between 10 raised to 22 to 10 raised to 28 or 27 meter square, whereas as the accelerating voltage increases, the scattering cross section keeps going lower and lower. This is kind of understood from the expression that has been shown. If I change the atomic number and I fix the accelerating voltage, you can see that as the atomic number increases, the scattering cross section is increasing. That is, for a heavier element, the probability of having a successful scattering event is much more than a lighter element. Also, as the accelerating voltage is reducing, you would have a larger probability of scattering. This gives you an idea that if I want to do some kind of analytical study on introducing lower accelerating voltages to understand the bonding or the inelastic nature of some of the specimens, I might want to intentionally reduce the accelerating voltage of an electron microscope and carry out analytical studies at a lower accelerating voltage. Nonetheless, for most of the inorganic specimens, you are typically operating the microscopes at 200 or 300 electron volts, and the scattering cross sections are reasonably well defined. As a ballpark figure, and to give you an idea, if I have an electron beam accelerated at around 300 kV, approximately 5% of the signal that is forward scattered consists of your inelastic scattering events. 95% of the electron beam undergoes elastic scattering, and most of this is more or less along the principal axis of the electron microscope. There are a few other factors which affect scattering cross section. The effect of theta, or the effect of scattering angle. For elements like copper, the angle of scattering increases from 0 to 180 as the scattering cross section decreases by several orders of magnitude. The effect of atomic number, I have just touched upon this. As the atomic number increases, you have a stronger interaction and an increase in the scattering cross section. The importance of accelerating voltage or the energy has been touched upon in the previous slide as well. If I lower the accelerating voltage, I am kind of increasing the scattering cross section. So typically, if I increase the scattering cross section, I can lower the scattering cross section by a factor of 2 to 3. So therefore, for a thinner sample, it is better for most of the element you would like to have thickness lower than 100 nanometers, so that you have the best combination of scattering cross section and the electron matter interaction. So to summarize scattering, we have seen scattering based on particle-particle collisions. We introduced cross sections and mean free paths. The Rutherford differential cross section explains the dependence of scattering on atomic number. When we talked about the wave nature of scattering, the coherency of the electron waves actually is directly related to the angle of scattering, and most coherent electron waves are very close to the principal axis. And how is this valid for real specimens? In reality, in a transmission electron microscope, the electrons are typically scattered through small angles lower than 3 degrees, and the intensity of the scattered electrons is strongly affected by the arrangement of atoms. So here is where the atomic scattering factor scales up to something called as the structure factor. If I have a periodic arrangement of atoms, the intensity of a successful scattering event is strongly influenced by the arrangement of atoms, and the collective nature of this is well understood by the wave nature of electrons. So scattering, to summarize, is mainly controlled by these parameters: the angle of incidence of the electron beam to the plane of the atoms, the separation between the atomic planes, which you will see in the Bragg's diffraction, and the interatomic spacing between the atomic planes. Also, we did not go into the periodic arrangements and the structure factor. This we will touch upon when we introduce electron diffraction and we try to understand diffraction. The concepts of Rutherford scattering cross section, the nature of the elastic or inelastic interaction, are important to also understand your inelastic signal or to understand EDS or yields when you are looking at advanced analytical techniques in TEM. You can also look at scattering or interaction in terms of projected potentials, which I will introduce to you very shortly. So, based on the Rutherford scattering cross section, we have established that the successful scattering event is when there is a deviation in the path of the electron beam. Now, the other way in which you can look at an isolated atom is you assign an electrostatic potential to this particular atom. So, let us say we have an atom. You can look at it as an isolated charged particle, and naturally this would have some kind of a Coulombic field due to this. And if I say that this atom in space has a radial potential which can be given by, in order to estimate this Coulombic potential, let us say you have an atom of an atomic number Z. You can assume the electron clouds of this would have a electrostatic potential as minus ZE, and the nucleus would have a potential of plus ZE. And you can write this in the form of an expression like this, an inverse, not really inverse square law, but inversely proportional to the radius surrounding the atom. Now, what happens when an electron wave, let us say I have psi is psi naught sin e power I phi, interacting with a potential like this. This would naturally cause a deviation and a deflection from what we understood from the successful scattering event, and in turn it results in a phase shift. You can in principle quantify these phase shifts, and if you look at the optical equivalent of this phenomenon in terms of wave optics, we define this deviation as a consequence of refractive index. But in terms of charged particle interactions, you can also define an equivalent term to refractive index in terms of the radial distance as where V is VR, the potential. This is actually defined as the Wenzel's potential, and E is my accelerating voltage of the electron. So, we have an equivalent of refractive index, and this, when I plug into the exponential term here for the phase, I can in principle relate the phase shift caused due to the interaction of electron beam with an isolated atom in terms of the accelerating voltage as well as the potential from an isolated atom. So, what you are trying to establish here, when I have a periodic arrangement of atoms, I call this as projected potential. There are the phase object approximations. In fact, for a reasonably thin specimen, you can look at atoms, isolated atoms or group of atoms, as sort of phase shifters which cause a change in the phase of the incoming electron beam. So, suppose I look at a schematic of the atom which is causing a modulation in the phase of the incoming electron wave. if I represent the electron as a wave which is written in the form of e power I phi, here it is explicitly written as e power 2 pi I kz z, because of the Wenzel potential which is defined in terms of the square root of accelerating voltage plus the projected potential over the accelerating voltage again. In the previous situation, I have only shown you the potential as a scalar there, but in reality, the potential varies over x, y, and also the thickness z. So, as a consequence of interaction with the isolated atom, if I now introduce the phase shift in similar analogous to the terms of refractive index in wave optics, this should cause a deviation in the phase of the scattered wave in terms of the projected potential being the phase shifting term here. If I look at it on how the phase shift is caused, for a single isolated atom which has a potential Vr, I can introduce a small phase shift in terms of the reciprocal coordinates as well. If I have the atoms stacked in a periodic fashion, and if I say u and v are the coordinates in the reciprocal lattice here, if you recollect the phase shift that is caused, and if I am looking at the projected potentials at the back focal plane of the objective lens, I can relate the phase transformation in terms of the, I can relate the phase modification in terms of the Fourier transform as well. So, if I look at the overall phase shift that is caused in 2 dimensions because of the atom having a potential Vr, if I integrate it, I end up with an expression for projected potential like this. And like I was just mentioning, the incident wave undergoes a the incident wave undergoes a Fourier transform at the back focal plane, and at the image plane I again have an inverse Fourier transform. So, the scattered wave vector can be represented in terms of an equation like this. In fact, you can introduce the terms from the Rutherford scattering cross section over here and build on to the whole thing to explain the contrast mechanisms as well. But this is to just give you an idea that when I have an electron wave interacting with an isolated atom which has a potential like this, I can introduce an equivalent of refractive index in terms of the projected potential from a collection of atoms which are arranged in a periodic fashion. And we know that the function of a lens is to first cause a Fourier transform at the back focal plane, and when it propagates further at the image plane, you have the inverse Fourier transform as well. So, the scattered wave I can write in terms of the projected potentials. In addition to visualizing the scattered wave in terms of the projected potential, you should realize that the presence of the specimen causes a phase shift. The phase shift can not only be caused by the influence of the specimen and the electrostatic potential of the specimen as well, but also you have an electromagnetic lens which can change the focal length. You have 2 effects here, the effect of the focus and the effect of the specimen as well. And if I look at the effect of the focus in the next schematic, if I have a lens where I place my object at S initially, and simply by changing the focal length of the electromagnetic lens, if I have a new position at S prime, initially if I have a wave which is resulted, and if I call this as epsilon d, because of the change in the phase, I am introducing a small phase shift here. So, if I look at the small phase shift that is caused due to the change in the focus of the electromagnetic lens, this introduces a small path shift, and let us say I am representing this in terms of the path shift introduced by the influence of the lens and change in the focus. Let us say the distortion of the phase or the phase shift that is introduced due to the defocus is given by an expression d chi. I can write it in terms of the path shift which is caused here as 2 pi over lambda times epsilon dr. Now, plugging in these values into the wave equation in 2 dimensions, where I have the projected potential as a function of x and y, the phase shift that is caused due to the object can be written as something of this form, where I have the defocus, the position of the atoms that are causing a phase shift, and the thickness of the specimen as well. So, I think with this you have a fair idea that due to the propagation of the electron beam in presence of an electromagnetic field and due to its interaction with a specimen which has an inherent electrostatic potential, you are introducing a phase shift. So, to summarize, electrostatic potential of a specimen introduces a phase shift. You should also remember the concepts from Rutherford scattering, where we've looked at the particle nature of the electron and denoted the successful scattering event in terms of an angle of scatter. Here, when you're looking at the wave nature of the electron, you are kind of introducing a phase shift, and the electrostatic potential of your crystalline sample is introducing a phase shift. And in addition, the phase shift can always be written in terms of the defocus, the atomic number, the thickness of the specimen, and so on. And there is one important term which I did not introduce yet, is the aberrations of the lens. There are several lens aberrations which we briefly touched upon in the lecture on electron lenses. You can always look at an aberration as a phase shifting term in addition to defocus and the specimen effects as well, and based on the kind of the aberration, you can always correct for them by using an aberration corrector. This is a topic which I will discuss at a later stage. To summarize, when an electron beam is interacting with a specimen, you can start learning about the scattering events by looking at the case of an isolated atom. And when an electron beam is interacting with an isolated atom, you can look at the Rutherford scattering cross section, through which you can start the fundamentals or the foundations for the mass thickness contrast for understanding the contrast in conventional bright field images. If you look at periodic arrangement of atoms, you can also look at interaction in terms of the electrostatic potentials, and this electrostatic potential, when you have for a group of atoms arranged in a crystalline fashion, you can look at it in terms of a phase shift that is introduced into the scattered electron wave. With that, I'd like to end this discussion, and moving forward, we will look at lens aberrations and how the phase shift is caused because of these lens aberrations and how the contrast mechanisms arise. We will first look at simple contrast mechanisms for bright field and dark field images, And then we will look at contrast mechanisms for high resolution TEM images. And eventually we will look at other modes of operation such as STEM. And once we know how the image is formed in each of these modes of operation of the microscope, and we understand how the information we get from these modes of imaging, you can get to know more and more about your specimen. Thank you.